Morning, everybody. So my role at Ingredion is I'm on the corporate global engineering team, and I do a lot of data engineering and data-related things related to our manufacturing facilities. So just a note about Ingredion, you probably haven't heard of us. We are a business-to-business food ingredients company, similar to an ADM or a Cargill, except smaller. We have about 50 some odd plants globally, about 12,000 employees, and primarily we're a corn wet milling business. That's kind of our legacy business, and our business strategy is really to focus on specialty starches and specialty food ingredients. So we're building facilities such as pea protein facilities, fruit extracts, specialized texturizers and modifiers. We also do have an industrial starch business, so Georgia Pacific is one of our big clients. We send a lot of cornstarch to you guys for your paper making. Yeah, great relationship. And one thing that I really appreciate as an Ingredion employee is Ingredion has been publishing their sustainability annual reports since 2011. So for over 10 years, the 2021 report is the latest that has been published. And our CEO and the executive team have they have very aggressive sustainability goals that they've put to the street, as they call it. So from a manufacturing perspective, sustainability, water intensity, CO2 reduction, waste are all key goals, like in our performance goals, which is a really great thing. And we're on a good track. Excuse me, we're not there yet. They're very aggressive targets, especially around water intensity. So we have plants in places like Mexico, which are very water constrained. We literally truck in water to some of our plants. And corn wet milling, similar to pulp and paper, very energy intensive. It's a wet process. So we take corn, we steep it like we steeped tea and separate it to get the cornstarch. And then we have to evaporate all this water. So after corn, energy is our second biggest cost. So what I'm going to talk about today is kind of go into some details about what Ron mentioned about applying AI in operations. My talk is about what we did in a London, Canada facility about having a machine learning model predict the set points of a series of cogeneration boilers. And this is kind of the summary slide, and I'll go into this, but in London, we have 3 5-megawatt cogen sets, so natural gas-fired turbines with boilers to generate steam. And in 2016, they were retrofitted or replaced with new turbine sets, and that allowed excess power generating capacity. So the question came up, hey, we used to run these things flat out all the time, 24/7. Now we have some excess capacity. What's the best way to operate these things? All the same time, or maybe there's a better way. And also at that time, our CEO, or the president of North America, Jim Zally at the time, he said, hey, big data is kind of approaching us. We should wrap our head around it. Go do an experiment. And I'm based in London, so we did it on this. And to make a long story short, it was a very successful experiment. Kind of in looking back at hindsight, we had a project that we could measure the savings, so natural gas. We ended up working with Canvas out of Toronto, so we had kind of a specialist that could help us with the machine learning models. And we went through several phases where we're saving 3% of our natural gas costs by dynamically controlling the boilers. It's basically a load balancing problem. So it predicts which boiler should be making how much steam, because the system is connected to a bunch of energy recovery systems and all these ancillary systems. So basically, cogen is an engine with natural gas, which spins a shaft to generate electricity. So we do that. And then the hot exhaust gases go into the boilers. There's not enough exhaust gases to make all the plant steam that to meet the load. So we have things called duct burners, basically big barbecue lighters that we just fire into the boilers to meet the demand. So our initial question was, can we optimize the turbines and the steam with working with Canvas? We did some back testing, and we found that 85% of the cost savings is in the boilers and the steam system. This was also kind of good because we couldn't pipe into the turbine controls anyway. A turbine, like power, generator reacts much more quickly than a boiler system does. So we couldn't have done it even if the opportunity was there. We just didn't have the controls ready. So we focused on the steam. We did write a white paper about this with Canvas. So if for those interested, we can get that to you. But there's basically 3 steps. So number 1 is you gotta get your organization ready, right? So you gotta get the people on board to try to make a change. Change management is probably 70% of the work. And preparing, our data systems and getting data. Number 2 is actually, training the model, applying AI. So Canvas was a huge help with that. And then number 3 is piping those predictions into the control system so that this could run in automatic mode. What makes a good AI kind of use case? I hear this a lot. It's like, how do you measure, the ROI of an AI project? And the answer is you need something good to measure. So measuring time is a very hard one. It's difficult to justify that. But measuring natural gas in a boiler, fairly straightforward. We can calculate it very accurately using math that everybody kind of can understand. The other thing is, is there data and instruments around this kind of problem? In a cogeneration system, there's lots of instruments, there's lots of data. We had lots of historical data. And I'll go through the architecture of how we do that. We also, safety is always the top priority. So when we were predicting, how do you actually make a prediction? You're not gonna send a signal to a gas valve, make it open more or less. You do it, you predict the set points, so something that a human currently changes. And if you have a model do that, the control system actually executes that set point safely. So we're not touching the control system. We're really only passing a predicted set point to a control loop. And then what we're thinking about now is with AI problems, what we don't want to do is try to tackle an application that is very, very unique. We want to tackle applications that we have. If we figure out a framework to apply AI in operations, we can do that 20 times at our plants. So we're going after things like optimizing our ion exchange columns, our spray dryers, and assets that we have dozens of. And with respect to this use case, it's really a load balancing framework. So the next thing we're using this for is things like RO water units, which kind of run in parallel. So it's load balancing can be applied to many problems. With respect to the team, it's really kind of 3 categories. The most important is the operations team, getting the plant on board. And in Canada, the operators that operate turbines and boilers are regulated. So there's a chief engineer, as it's called. So getting his buy-in was critical because we are kind of working in the powerhouse. We can't just play around in there. He was on board from day one, and his operations team as well. And then the kind of the digital team, so people working with the data engineering and the systems. And then the IT, really, they just, make sure that our kind of infrastructure works we're on Microsoft Azure, so we use some services there, which I'll show you. So the architecture obviously starts at the plant, in the process network. So, all of our plant plant sensor data goes to AspenTech IP21 process historian, similar to OSI Pi, and our company has standardized on that. So that's kind of in the business network. We have lots of historical data in Aspen, and what we do is use a service called Azure Data Factory to query that Aspen data using SQL and pass it to a third-party model, in this case Canvas, and we just pass it to their blob storage. Okay, so every minute we're taking 100 tags at the minute level and just passing it to Canvas, and then they're taking those tags that we've identified as kind of being important to make a prediction, and they're putting it into their model. So I don't care about the model. I just care that it predicts something that is useful to me. I want a model as a service. I don't want to maintain the model. I don't care about that, quite frankly. What I care is that the model is doing something good, and they're taking care of it. The other kind of important part is piping this back into our control system. How do you do that? So we run a Python script that connects to their cloud and pulls it into our business environment first, just into a SQL database. And we average the predictions to get one 15-minute set point. What we found early on was that trying to change set points in a boiler system every minute is way too frequent. And a sweet spot is, changing it every 15 minutes. Before, like in phase one, we actually had the operators changing the set points that they saw manually every 4 hours. So this was not a closed loop. And we found a little bit of benefit on that. And then once we piped it in that this is happening every 15 minutes is when we kind of found our real benefit of about 3% cost savings. So the way we get that into our control system is we have a very kind of basic SQL database in the process network that can do very, very limited things. It can only pass, these values to these tags. And the reason we did that is, security basically. So even if somebody, gained control of this database, it really can't do anything other than pass a set point, to this very particular thing. So that is our approach. It works. It's reliable. There's probably other approaches to do this, but here's one. So a little bit on the models. So there's actually 4 models. And this is kind of where working with somebody who understands kind of the modeling is important. So when we were discussing this with Canvas, they said, hey, every boiler needs a model, and we'll train each boiler independently on its own historical data. And then we have a 4th model that is basically an optimizer. And it basically just enumerates, 100,000 times to find kind of the minimum, point, which is kind of the highest, the lowest natural gas consumption to meet steam demand. If that makes sense, okay? So, when people say like a model, it's typically a series of models, and these models, they may not be the exact same kind of algorithm, types of models, right? So it's important to kind of understand these nuances of modeling. And that all kind of lives in Canvas's instance or a third party. This is just how we kind of set up the problem. So we try to kind of create this optimizer to identify the minimum natural gas flow to meet steam demand based on multiple boilers. And here are some of the key kind of driving tags. Steam flow. T5 is kind of the temperature coming from the turbines, and then things like drum pressure. Weather actually we found makes a big impact. So at night humidity typically falls a little bit. So the boilers, the model predicts a little bit of a different operating way. and we have our cogen system, the exhaust gases go to, like, one boiler sends it to a hot water system, to recover the exhaust gas from the boilers, to warm water. Another one sends it to a fiber dryer. Another one does something else. So you got to look at all these layers, right, to kind of get efficiency. It's not as simple as, a control loop in your boiler control system that can do this, because there's kind of auxiliary systems in the plant that affect the efficiency of the entire thing. So this is what things looked like before predictions. So you can see, the boilers operated about the same, right? So, when plant demand, steam demand went up, they all kind of went up equally, down equally, et cetera. This is just showing the same thing. They're all kind of operating about the same. This is the predicted steam flow. And what it's showing is that, one of them should just be a baseline boiler, like go flat out. And because it's connected to these auxiliary systems, like that's your most efficient boiler, right? So just run that one hard 24/7. And then there's a second one that run that one hard. The third one has to run, like you can't, there's a minimum that a boiler has to do, right? So that's kind of what it's doing here. It's one is kind of the base load. The second one is meeting, the second most efficient is doing as much as it can so that the third can operate in a minimum, which is the least efficient boiler, okay? So that's kind of the big insight that we found was, this operating model. This is just how the steam, another thing it looks like. Another good thing that we did was, because we had a lot of historical data, is we kind of, separated that data set that we could back test the models to see, hey, if we had run in this dynamic way, how much money is on the table here? Which was important in justifying a project, okay? So the size of the prize, this is like 2017, so natural gas price was like $2.50, right? Was, enough, $400,000. And, now it's like $10, so, it's saving a lot of money. But that was also a useful thing, is that we could back test the data. And then this is just kind of showing you, the predicted gas flow at the top is kind of dynamic. Without the predictions on, the graph at the bottom, you can see, two boilers are kind of operating the same, and one is a little bit lower. And then once we have, dynamic control on, is it followed it fairly closely to the system. What I'm showing here is the control system could keep up with the predictions, okay? And that's kind of when we started seeing our benefit. This is a few kind of classes of operating mode. This light blue one was, before any predictions. So it has the highest cost of steam. Something that is kind of like counterintuitive, but once we saw the insight of, hey, run one base load and then, 2 and 3, like you could run that in manual mode without the AI actually and get some benefit. So even just going through the exercise of, without deploying it into, a closed loop, before we had a closed loop, like the operators just started running it that way and we saw some savings, right? So that was kind of something we didn't expect, is just, hey, the insight from even just going through the exercise of trying to come up with a model told us this is how you should operate it. And then in predicting mode, you get a little bit more benefit as well, right? So we also did kind of try to duplicate this idea internally. IT wanted to save a few dollars, to do this internally. What we found is we spent a lot of time on it, but there's really not that much, diminishing returns here, right? And this is something, I would recommend is, once you find something that works, move on to the next problem. There's so many low-hanging fruits at a plant, right? Trying to optimize, there's a point of diminishing returns here. And I think the bigger value is, deploy, measure, and move on, right? Because these things take time, and like the limiting factor is typically not like dollars. It's really human time, right? And your teams. So here's kind of in conclusion a few things worth noting. Start with going after problems that you can actually measure benefit. Energy is a good one. Water, things that you can measure. Your data engineering, your architecture is very important. Like if you can't get good data, you're not going to get too far with kind of the modeling part. And I think the control system, piping it into your control system is also, very important, because you do see the benefit of that. If you don't have to rely on operators manually changing set points, like that's kind of the name of the game. And then think about problems that you can scale. We have this framework of load balancing now in our heads. So we're trying to apply that to other load balancing problems. So things that are running in parallel. What's the most, just asking the question, what's the most optimum way to run those assets that are running in parallel? And that is everything. Any questions? Oh, after.